propagation in the 5th lecture today, and will complete the course. This will complete your course. So as we know that this becomes an anisotropic medium when we have the magnetic field present. In the presence of magnetic field, it became an anisotropic medium. Now you can ask me why it became an anisotropic medium. We have seen in the previous lecture in the Maxwell's equation, we used curl of H is equal to j omega d or minus j omega d. Instead of using minus j omega epsilon 0 E, we used minus j omega d. Why we did that? Because d is equal to epsilon 0 E plus P. That is the part. Now P is changing with direction. Therefore, epsilon r is changing with direction. In the presence of magnetic field, epsilon r is changing with direction. Since epsilon r is changing with direction, it is not constant along all directions. Along x direction we will have epsilon rx, along y direction we will have epsilon ry, along the z direction we will have epsilon rg. Therefore, we are not having isotropic value, same value in all directions. It is not isotropic, no more isotropic, it is anisotropic. If it is anisotropic, it will have different values in different directions. So my ionospheric medium is in the presence of electromagnetic magnetic field, it becomes anisotropic. So we have considered an anisotropic medium. In an isotropic medium, the phase velocity at any given point is independent of the direction of propagation. It remains constant. As you know, free space is isotropic. Air is isotropic. In air or free space, the phase velocity is c, right? So it is constant along all the directions. For isotropic medium, hello, go.
Sir, slide is not visible.
Slide is not visible. Okay. Let me move the slide. Anisotropic medium, is it visible? No, nothing is visible.
Nothing is visible.
Okay. Other circle. Is it visible now?
Yes, sir.
Okay. All right. Okay. So for an isotropic medium, the direction of the phase propagation, that is movement of equiphase plane, phase propagation is equiphase planes in which direction they are moving, that is radial with velocity. We are considering here the velocity u, so up is the phase direction, so that will be radial with that. The energy propagation, which is generally taken as the group velocity, and that is also radial in case of isotropic medium. But if you go to anisotropic medium, the directions of equiphase plane and energy, they are not same, they are different. So they will be in different directions. So equiphase plane and energy, they are in different directions. Now let us start with an isotropic medium. Okay. There will be isotropic medium. In the isotropic medium, as I told you, the wavefront is circular. So in the pictorial form, let us look at this. Circular wavefront will be there. So if I have the point source, from the point source at a distance r from a point source, everywhere on a circle or on a sphere surrounding the point, where the point is at the center, the phase is constant. Therefore, the moment phase velocity is constant everywhere. It will be moving with the same velocity. So if I take any r is equal to r0, r is equal to r1, r is equal to r2, everywhere it is from r0 to r1 it goes with velocity, phase velocity up. From r1 to r2 it goes with phase velocity up. Now how do you find out what is the direction? What we do is, on the surface of the wavefront we draw a tangent to the sphere or to the circle, and to that tangent it will be perpendicular. So it should be the velocity is perpendicular. Now if the velocity is perpendicular, in case of a circle here or in the isotropic medium, since we are having a circle, perpendicular to the tangent of a circle or a tangent perpendicular to the tangent of a sphere is its radius. Therefore it is always radial. So phase velocity is radial, energy is always, as you know from the source, energy propagates out in the radial direction. So propagation direction is radial, distribution is perpendicular to radial, but propagation is radial, and therefore energy is propagating in the radial direction and phase velocity is also in the radial direction, because phase is increasing in that direction. So that is for the isotropic medium. But if we consider anisotropic medium, then the surface is no more a sphere. So non-circular wavefront. If I have got a non-circular wavefront, and then the propagation direction will be radial. Always it is going in the radial direction, but the velocity always will be perpendicular to the wavefront. So the propagation direction and velocity, they are not going to be same, they are different. Now propagation direction is radial, and propagation direction determines the energy propagation, in which energy is going, right? And wavefront is normal, that determines the phase velocity. So in that direction, normal to the wavefront, the phase is constant, so there is the phase direction, and propagation direction is the energy direction. Now this the velocity along the propagation direction is called the group velocity. So along that the group velocity goes, along on the phase goes the phase velocity. The group velocity is the velocity of propagation of packets of frequencies which are centered about the carrier frequency. So whatever frequency you are using, suppose it is f0, then f02 plus minus delta f on both the sides, that is the band of frequency. So packets of frequency around the center frequency, the velocity of propagation contains that. For simple amplitude modulated waveform, if we are using that, then this is the velocity of propagation for the envelope. Envelope means envelope of the modulated wave, amplitude modulated wave. You know, have you read amplitude modulation? I hope you have read amplitude modulation in communication. In the amplitude modulation, what you have a carrier wave which has high frequency, then you have a modulating wave, and the carrier wave is modulated, the envelope of that modulation or the carrier wave after modulation follows the modulating wave. So here it is the velocity of the propagation of the envelope, whereas the phase velocity is the velocity of the propagation of the carrier waves. So that is what happens in case of amplitude modulation when you are in the anisotropic medium. Now we will try to find out what is the phase velocity and what is the group velocity in ionosphere, if we are considering ionospheric propagation. Now by definition we define phase velocity as omega upon beta, and that you can write as c upon n dash. N dash is the real part of the refractive index. You can do that easily. Omega by beta is equal to c by n. That you can easily do, because omega upon beta is equal to c by root over of epsilon. So from that you can do that. Then Ng into Ug, Ng is the group velocity, Ng into Ug is equal to c. Ng being the group index diffraction and Ug is the group velocity, right? So for the group propagation or for the energy, refractive index is Ng and Ug is the velocity. Now from this you can see that Ng is equal to Cg by Ug, because Ng into Ug is equal to C. So from that you can say Ng is equal to Cg upon Ug. That is equal to C remains as it is. Ug is defined as d beta upon by d omega. So differentiation of beta with respect to omega. Differentiate beta with respect to omega, that gives you this. So that we can write as differentiation with respect to omega of 2 pi c by lambda. So from where this we get? C remains as it is. C is independent of an omega, so you can take c into the differentiation. Then beta is 2 pi by lambda. So d omega of or d by d omega of 2 pi c by lambda. That we can rewrite as 2 pi c by lambda remains as it is. That into 1. Now n dash up by c is equal to omega by 2 pi f. So we can write n dash up by c into omega by 2 pi f. So that will make it 1. N dash up, now you can put that value also here easily. N dash is equal to c beta by omega. So put that n dash first, n dash put c beta by omega, c cancels out. Then up accordingly cancels out. So already you get 1. So this you can write as, if I cancel out 2 pi cancels out, then omega cancels out, omega remains as it is. 2 pi cancels out, c cancels out. Then n dash up by lambda, that cancels out. N dash remains up by lambda 2 pi f, that cancels out. So ultimately we are left with n dash into omega. So d by d omega of n dash omega. That is equal to, from that you can write Ng is equal to n dash d by d omega of n dash omega, that it will be n dash d by d omega of d omega plus omega d n dash by d omega. Now omega is 2 pi f, so that will be 2 pi f. D omega will be 2 pi in df, 2 pi into df. So 2 pi cancels. Ng is equal to n dash plus f d n dash by df. So this is the group velocity. Phase velocity we know up is equal to omega by beta or c by n dash, and group velocity is now n dash plus f d n dash by df. And now from this let us try to find out what is the total electron content. And now that we know the group velocity, let us find out total electron content. N dash is equal to root over of 1 minus x. This we have seen earlier when we started the study on ionospheric propagation. So n dash is equal to root over of 1 minus x. Use binomial expansion, so that will be 1 minus 1 by 2x, approximately equal to 1 minus 1 by 2x, which is equal to 1 minus 1 by 2x value. Value of x is n square by m epsilon 0 omega square. Put values of epsilon e square, m, epsilon 0, then 2 pi square, which is 4 pi square. Put those values, that will give you 40.3 Ne by f square. So n dash is equal to 1 minus 40.3 Ne by f square. Refractive index, real part in ionospheric medium or ionosphere is 1 minus 40.3 Ne by f square. That is approximately 40.5 Ne by f square. From that you get this 81 terms comes from that. Now Ng is equal to n dash plus f dn dash by df. So use that. N dash remains as it is. Ng is equal to, using these values of n dash is equal to 1 minus 40.3 Ne by f square. So put that 1 minus 40.3 Ne by f square plus f into dn dash d n dash by df will be 40.3 Ne by f square d by df of 1 by f square. So take that. Using those values, you will get this. It will be equal to 1 plus 2 40.3 Ne by f square, which is equal to 1 plus 1 by 2 x. And that you can also write as 1 plus 1 by 2 x is 1 upon root over of 1 minus x. How is that? Again binomial expansion. 1 upon 1 minus root over of x is 1 minus x to the power minus 1 by 2. 1 by 1 minus x to the power minus 1 by 2 is 1 plus 1 by 2 x approximately. So 1 plus 1 by 2 x, and that comes. So that will be again, as you know, root over of 1 minus x is n dash. We have already seen that. So that is 1 by n dash. So ng will be approximately equal to 1 by n dash. And then let us define phi. What is phi? As minus omega by c p1 to p2. p1 to p2 is the path that the electron moves within the ionosphere. So it starts from p1 and ends at p2. And then the phase difference phi in moving from p1 to p2 is, as you know, phase difference is equal to 2 pi by lambda into path difference. So we are finding out the phase difference, that is 2 pi by lambda into path difference, or 2 pi by lambda, that we can write as 2 pi f by lambda into f. Now lambda into f is equal to c, 2 pi f is equal to omega. So this will be minus omega upon c. 2 pi by lambda is omega upon c. So that into path difference. Path difference we are taking from p1 to p2. So from p1 to p2, path difference will come from this value of n dash. N dash into ds, that gives you the path difference. Right? So that will be 1 minus 1 by 2 n square by m epsilon 0 omega square ds. This comes from path difference. How it is coming? N dash ds, that comes from the principle of least action in light. In physics, there is a principle called principle of least action that says that if light is propagating, light is equivalent to electromagnetic wave. So if electromagnetic wave is propagating from point P1 to point P2, then the path covered is minimum, and that is given by n into ds. ds is the length of the path. So end points are P1 to P2, minus of that. So that gives you this. Now integrating that with respect to ds will give us minus omega by c l, that comes from the first part, minus omega by c integration p1 to p2 1 ds. So that gives us minus omega by c into l. p2 minus p1 is equal to l. So minus omega by c l plus minus minus plus half n e square by m epsilon 0 omega square. Now Ne is integrated over that path, that gives you the total. Ne is the density over the path, that will give the total number of electrons in that within that path, contained within that path, that is empty. So phi will be this one. So from this we will see that total electron content Nt will be equal to this integration of P1 to P2 NES ds. That is the total electron content. So now we have found out what is the total electron content once we know what is phi. And now phase delay and time delay. When it is propagating in this ionic medium, what is the phase delay and what is the time delay over a path. Now phi, we have found out the phase difference is omega by c l root over of epsilon r. That we also saw, that minus omega by c n dash l, which will be beta n dash l, which is minus beta l. N dash l we can take as l. N dash is equal to 1, approximately 1. Time delay is 1 by c into P1 to Pt 1 upon n dash s ds. How do you get this time delay? Why this definition? Now time, time and path, they are related. Path and time, there is a relationship between path and time. What is that relationship? What is the relationship between path and time? That relates through velocity. Now v and t are related. V into t is equal to the path traveled. Right? So t is equal to path traveled by v. So from that we get this. Td is equal to time delay will be this much. Okay. Now doing the integration for this, we'll get for n dash s, we'll put 1 plus 1 by 2x ds. So that integration will give us L upon C plus 40.3 nt upon C f square. Now once we know what is Td, then we can find out what is T0, phi0. Phi0 will be equal to minus K0L plus the rest of the part that is shown here. This part we have already seen in the formula for n, when we have found out the n dash formula. Let